dear colleagues, it's a pleasure for me once again to be able to speak with the ESSA convention. Last year when I received the invitation, I was very much hoping to be there in Manila in person, and we never thought that we'll be doing another online conference. But in any case, it's really my pleasure and honor to be able to speak on this forum once again. So today, the topic of our discussion is on the challenges that we face as engineers in modeling of structures. Now, what I want to emphasize is that the challenges that we are facing are in fact not necessarily related to the complexity of the structure or the size of the structure, but rather they are intrinsic in the very basic concepts of modeling when we represent the structure into different forms and we do the analysis. So I have decided to take the approach of identifying some of those challenges through very, very simple examples. And those examples are so simple that one would not imagine that there will be so many challenges in trying to model them accurately. And you will see that we will start with the discussion with a single beam resting on two walls and see how difficult it can be if we want to model that accurately and analyze every aspect. And after that, we will move on to a frame, simple frame with two columns and one beam, reinforced concrete frame, and see what other additional challenges we have when we try to model reinforced concrete structures with rigid ends and with ductility and so on, so many other things. So that will give us some idea of the challenges that we will face in buildings in general. And then after that, we will move to two important topics which are related to the portion of the structure which is underground, which is the foundations and the basements. And this will bring us to the challenges and the importance of soil structure interaction, as well as able to model the foundations more realistically and more accurately. I should not say accurately, more realistically. After that discussion, we will also talk about two slightly advanced models which capture two other important aspects in structural analysis. One is the construction stages, because structures are not built instantaneously. They are built over a period of time. How does the construction stage and construction time affect the analysis and the results that we get? And then finally, we will have a short discussion on the importance of nonlinear dynamic analysis. But in reality, every structure becomes nonlinear at some point, especially reinforced concrete, and especially during earthquakes or strong ground motion or even in blast and other conditions. So ignoring those two aspects it means that we are not really capturing the expected response of the structures. So we'll be discussing these few topics, and I'm going to use some of the videos that we have been recorded on these topics earlier, and I hope that you will find them interesting. And in the end, we will have open session for discussion. So let's watch some of the discussion on these topics. Like I said, I'm taking a step back. I'm not taking a very complicated example today. I'm going to start with a very, very simple example of a structure. Just a beam resting on two walls. Nothing can be simpler than that, right? And if we can model this properly, we should be able to move forward. You might say you don't need analysis or modeling to determine the response of this structure. I can do it by hand, by WL squared by 8 or WL by 2 or something like that. Completely true. We don't need a computer modeling to solve this problem. But let's say if we had to model this structure completely and properly, what will be the challenges? So first of all, we would like to model this structure realistically and calculate its behavior for different excitations, not just for vertical load. So let's see what are we talking about in that context. So basically, we would like to represent the materials realistically. Now this is a reinforced concrete beam. We have rebars in there. We have the two different materials putting together. We have a masonry wall there, which is made of brick blocks, which has mortar in there and so on. We have supporting system, foundations. So can we model all of those materials realistically? Can we represent the geometry correctly, realistically? That means it captures the behavior. Can we represent the connectivity between these elements? How is the beam resting on the walls? What is that connection? Is it pin? Is it roller? Is it spring? What is it? How do we represent that simple connection where the beam is simply resting on the top of the wall? How do we capture the invisible behavior? For example, friction between the wall and the beam, or the sliding of the beam, or falling off of the beam. Right? How do we do that? And then how do we understand the response that we will compute and make some decisions that are useful? So let's get into it. Let's see, number one, the simplest case. In the case where we have a vertical load on the beam, and how do we calculate the response for a vertical load? And that is obviously the simplest case. And then what anybody will do is that they will take this beam and they will put it on a roller and a pin support. Probably they will model it like that, apply the vertical load, and then easily calculate the bending moments and even deflections and shear forces and all. There doesn't seem to be any problem with that. But look at the first problem. When you model it, you model the center line of the beam, which is actually far from the real support of the beam. It's not the same location where the beam is in contact with the wall. So you're modeling a beam center line which is away already from the real support, and that will start creating the problem in our modeling. But okay, let's forget that for a minute, and we can do this model and we can get the response for the vertical load. So we use the concrete modulus of elasticity. We use average models. We neglect the rebars. We just assume it's a concrete. And we use the initial elastic model or tangent elastic model, or do we use the secant elastic model? There are many options there. So we have to make a choice on which elastic model we will use even at this point. And then do we use gross cross section, or do we use the cracked section? Because when you apply the loading, the beam will crack, and then the cross section will change along the length. It will crack more in the middle, less close to support. So which cross-section properties should we use for calculating the response, the deflections, for example? Then let's say we use the line element or a frame element to model this one, and like I said, we put it on two support, one roller and one pin. Which side should be pin and which side should be roller? Because in reality, both the supports are identical. The beam is just resting on the wall. So you are arbitrarily saying that one is pin and one is roller. Which one is which and why? So we'll come back to this again. And then, okay, then we apply a vertical load with a UDL. Again, whether it is applied at the top, at the bottom, of the center line, that's a question, but let's say we assume that it is applied at the center line. And then we can do a linear elastic analysis and we can get the response. It's a simple thing, but as you can see, we already raised many questions here. Let's go to another case, next step. Let's say that the load is not vertical. Let's say now that the load that we are talking about is actually a horizontal load or a horizontal displacement. For example, there's a load coming from this side because of any reason, maybe it's earthquake movement, or there is a temperature change, or there is a shrinkage in the beam, so it is causing deformation in the beam, axial shortening or expansion. Now what do? Will that model that we just made work? For one thing is that if we use the pin and a roller condition, then if we have a pin on this side, if you apply the horizontal load, that pin will absorb the load and it will not go to the other support. But we know very well that the load from this beam, horizontal load, should be shared by the two walls. How will that happen? How will we model that? If you use pin here, roller here, then we already are in trouble. If we use both rollers, then we again are in trouble because the beam will simply slide off the walls and we will not get any reactions. What about when we have the thermal expansion? Then the beam is supposed to expand on both sides. What will it do to the wall? What kind of reactions will be induced? So will the walls provide enough restraint or will they not? So all these questions start to come up when we simply change the direction of the loading from vertical to horizontal. And now we cannot really model in a very simple manner without making several assumptions. Let's go one more step. And we say, okay, let's say the beam is like this one, we're looking from the side, and there's a wind blowing on that side, and actually it is trying to topple the beam. So there's a wind pressure coming from the side. Now we have a completely different problem to solve, because we need to see the centerline model that we made last time may not be relevant anymore, because first of all the beam center line is here, support is here, so we have a gap in between, and also in reality this beam might topple and overturn over the wall, but our centerline beam model will never tell us that can happen, because it is representing the beam at a center line which is supported on both sides, so it cannot topple, it cannot rotate in that way. Even it can rotate, it can only rotate about the center line, not about the top of the wall, which is far from the center line. So that means now our traditional simply supported roller pin model will not work in this case, right? And we need to go beyond that. Let's go further. So now you can see that there are several issues that have come up in this just because we changed the loading. That means we cannot seem to use the same model for different loadings, which should not be the case. In an analysis program, when you make a model, you apply different loadings to the same model. And in our case, we can see that it will not be the case. Let's go further. Okay, let's say that we realize that a simple centerline beam on roller and pin support may not be sufficient. Then what options do we have? Let's say we go to a computer program, and we say, okay, I'm going to model that as a frame. So I'm going to represent the wall as a vertical column, and that wall also as a vertical column, and I'm going to represent the beam as a frame, and then I'm going to create this frame. But the first problem again is that the beam will be modeled at the center line, and walls will be ending here, so there's going to be a big gap between the center line of the beam and the supports where the beam is actually resting. And so we have this offset between the center line and the supports, which now will create a problem. Either we lower the beam down so that the center line comes to the top of the wall, or we raise the walls up to match with the center line. Both of them are incorrect because they alter the physics of the structure. That means our frame model now has some challenge. Obviously, there could be many ways to solve that. We'll come to that in a minute. But you can see that even creating a simple frame model for this example runs into trouble right away. Then let's go to another option, a frame shell model. Let's say if the wall is very long, we don't want to represent it by a column, we can create a shell model of the walls to make it more realistic. And when we can represent the beam as a frame, and then we try to connect them. But that does not solve our problem, because there is still this difference between the beam center line and the top of the wall. That gap is still there, and we need to do something about that. But this model will be slightly better for the walls, but it doesn't solve the problem for the beam, and especially doesn't solve the problem of the connection between the beams and the wall. Right? But at least now we know that we have an option of doing a simply supported single member, we have an option of doing a frame, we have an option of doing a frame and a shell. Then let's say we want to create a complete shell model. Another option is that we go one step further, and we say, okay, we will represent the wall, which is it's a planar structure, by a shell element. We will also represent the other wall by shell, and we also represent the beam as a shell, because beam has a depth, so we can model it as a shell. And now we have solved a few of the problems, because the first problem we solved is that the connection or the support of the beam is now actually on the top of the wall. So that gap problem or the geometric inconsistency has been resolved, and we can actually place the beam exactly where it is, and we can model the geometry reasonably. But several other problems we have not solved. We have not solved the problem of the gross cross-section of the materials, and so on. And we haven't solved the problem of the connection between the beam and the wall yet. But geometrically, the model has started to look better, right? And we can have a good physical sense of the structure. Now, let's go to next step. And we say, okay, let me model the whole thing as a solid, so that because in the previous model, if I go back, we still have a thin shell resting on the wall, and it doesn't have
the stability on the transverse direction because of the something called the orphan degree of freedom problem. When the degrees of freedom of one object do not match with the degrees of freedom of the other, so some degrees of freedom are orphaned, so the connection will not be fully established. So to solve that and to solve other problems, we could say that, okay, I'm going to model everything as a solid element. In fact, mechanical engineers normally always model their structures as solids because they physically correctly represent everything. But in civil engineering, in structural engineering, we make normally a lot of assumptions and simplify the structures. So now we have a solid model. That means the wall is physically correct, the beam is physically correct, the beam is really sitting on the wall at the correct location, and the dimensions are now correctly modeled. If the beam is wide, it will be more stable. If the beam is narrow, it will be less stable, and so on. And same is the case with the walls. So geometrically, it's a very good model because the change of the cross-section will not change the results or will not change the assumptions, and it will just be correct. But the problem of the connection between the beam and the wall still not mentioned. And the other problem now we have created for ourselves now is that it is not easy to calculate the bending moment in the beam anymore, because the solid element will not give us the bending moment and shear as we normally get from a frame element. Now we only get stresses, and those stresses will have to be integrated, converted back into bending moments and so on, and those stresses are not useful for reinforcement design directly. We will have to do a lot of processing to get sense of what reinforcement we need. Also, it will be very difficult to induce cracking or incorporate some reduced stiffness into the solid model, because in a beam we can simply modify the properties by changing the property modifiers in shear and torsion and axial and bending independently of each other. There are 6 stiffnesses that we can modify to get the behavior that we want. In solid, we don't have that opportunity anymore. It's more or less complete. So even though we solved the problem of the geometry, we created problems now in the result interpretation, and we also created problems in the modeling of the properties or the modified properties. So while each model gets better in one direction, it gets worse in the other direction. And especially we haven't solved the problem of the connection between the support and then, because if you just connect it, it will become rigid connection, and the results will be very different from what we really expect. So if you look at that in a SAP, for example, you could make different types of models for the same thing. This is a simple beam. I represent it in an extruded form. This is a beam, centerline on wall, beam on shells, and then different models of shell on shell and full solid models. You can create them in SAP if you like. For if this simple structure, we can have several options and some disadvantages, and they can all handle some loading and cannot handle some loading. So none of the model is actually really solving the problem that we started with, and we started with a very simple problem of a beam on 2 walls. What can be simpler than that? So what we have learned so far is that even with that simple problem, it is very, very hard to model everything as we want, unless it's a thesis, master thesis, in which we are only doing this for 6 months or 1 year. But in a design, we have very little time to do that. So if you just look at the model, the way they will all have different response. Some will give you bending moments, some will give you stresses, and you can see solid models of different kind where we try to solve many problems of beam going to the end, not going to the end, and so on. And if you look at one parameter, the deflection in the beam, center of the beam in different models, you get different answers here from one to the other. Every model is giving you a different value of the deflection in the middle. And if you just use the manual calculation in the middle, some are higher, some are lower, and the variation is quite big. So the question is, which model is right? In this particular case, actually none of them is right, because in the deflection of reinforced concrete, we have to incorporate the cracking and the effective stiffness because of the reinforcement, and we have to incorporate the long-term loads, we have to incorporate the shrinkage, we have to incorporate the creep, we have to incorporate so many other things that none of these models can handle so far, which means that even with all of this, we didn't get the deflection right. We might get some of the forces right, we didn't get the deflection right. We didn't solve the problem of the connection between the beam and the wall yet. We only have few options. Either it's a hinge, or it's a pin, or it's a roller, but the real connection is a sliding member resting on top of the wall. So how do we do that? So that brings us to some other problems that we actually did not solve. First of all, like I said, the beam can slide on the wall, and we didn't incorporate that in our modeling. Sliding, friction. The beam can actually fall off from the wall. Our models will never show us the beam falling down from the wall, no matter how much load we apply. The beam will always be resting, will be connected, unless we use really advanced modeling. Then the other problem is when the beam rotates, we assume that the beam is resting on the center line of the wall. But actually when it rotates on the edge of the wall, not on the center line. So that means the span that we assumed is also not correct. And then actually that rotation at the edge of the wall will change the reactions, not from here, but to the edge of the wall. So those things we just didn't capture because we assume that we are modeling the things at the center line, and we have a pin roller at the center line. If the wall is very wide, this could be a big difference. Let's say the wall is half a meter on each side. So your span estimation will be off by half a meter. Deflection, moment, everything will be off by that. So many things, and some people will use clear span, some will use centerline span, but what is the real span, we don't know. And then the stresses around the edge, the wall, could be very high around this area. So you can imagine that how it will go. And then this whole thing, the sliding here, we have not been able to capture that properly also. Then to solve these problems, we have what we call the behavior elements. So because we could not solve this problem by physical modeling, because no matter how fine we made the modeling, for example, we use the solid element, shell element, whichever, we still could not capture the behavior that we were trying to capture because so many things we couldn't model. And that's why these behavior elements come to our rescue. And behavior elements include constraints. Constraints could be used to model the offset between the beam top and we could use rigid links. We could use springs, links, dampers, isolators, hinges. Links are the most powerful of these elements. It could be linear, that could be non-linear. So by using links, we could model the friction between the wall and the beam. We could also model the nonlinear falling off. By that, we could model lift, uplift, and we could model many things. So by using the appropriate links and other things here, we could actually model many of the things that we missed. So by combining a good physical model with good behavior elements, we could actually get close. But it's a lot of work for a problem as simple as that, and I'm quite sure nobody will actually spend that much time for a beam resting on walls. What is really missing? And if you really think about it, almost everything which is realistic in a real structure or a real response is missing from this analysis. And this is analysis that does not give us in-depth picture of the response of the structure. Real structure will be constructed by using the drawings that we make for it. The columns will have a finite size. There will be reinforcement here, as I mentioned, both vertical and horizontal. There will be ties, there will be confinement, there will be shear reinforcement, and everything will have some capacity, which means there's a certain amount of moment that the column can take, or a certain amount of shear the beam can take, and so on. Real frame will have finite dimensions, will have finite material properties and strengths, will have a limited deformation and force capacity. So it might actually yield, buckle, damage, or break. And all of this we cannot determine from the linear analysis that we just carried out, because that will give us unlimited displacement for unlimited loads without any of these considerations. A real frame will not be what we model, but will actually look like that. So you can see from here the vertical reinforcement, horizontal reinforcement. So actually this is what will be constructed, and this is the structure that we should be trying to model and get the response of. Let's go one step forward to the next stage and see what is it that we really need to do to handle the complete response. We need to handle the stability of the structure first of all. We need to make sure that the structure does not fall, does not slide, does not overturn, does not have a large deformation. We need to make sure that the strength and capacities are considered, and we should not be able to apply a load which is unrealistic, or we should get displacement which are more realistic and which are not unlimited. We should be able to determine the damage in the various parts in the concrete and steel. We should be able to calculate the energy dissipation because of the repeated loading or our seismic input. Long-term effects like creep and shrinkage, we should be able to handle those. We should be able to address the foundation settlement, salt structure interaction here. We should be also able to look at the local failures, for example, bond failure between steel and concrete and crack formation and so on. And we should ultimately be able to say something about the durability of the structure. How long will it last? Or what are the things that will make it unusable in the long term? So these are some of the considerations that we should be able to handle. Obviously, many of these things are quite complex, even with advanced modeling techniques. So let's start with two of the items in the list, which is stability, strength, and capacity, and see how we can look at these. The first model, which is a stability-aware model, will be able to consider the global buckling of the entire structure as well as local buckling of parts of the structure. So it should also consider the P delta, the moment magnification coming from the local deformations, and the large P delta, which is the moment magnifications or change in deformations coming from the global displacement. So these are the basic things that we should be able to handle. And we should also be able to handle foundation uplift, type of the foundation, fixed foundation, pin foundation. We should also be able to address overturning, sliding, and large displacement effects. So these are the things that we should be able to do in a model. Let's start again with the first part which I mentioned on the top and see how that will affect our response. So once we include the geometric nonlinearity in the model, so we will include the global P delta, which is the displacement increase because of the large displacements happening. The moments will be magnified, and that will magnify the displacement further. So this P delta effect, which is basically related to the lateral displacement of the structure, we can include those. The local P delta of the column and beam, we will be very insignificant for this example, so we will not consider that. And we will consider two options, the fixed foundation and pin foundation, to simulate different foundation conditions approximately. So if we do that, now we get nonlinear curves or response curves, not linear like last time. That means there is a limit how much load the structure will actually take. If you remember the previous graph, the load could be around 60,000 kilonewton for a displacement of 400. Here we can see that if we consider P delta with fixed foundation, the load carrying capacity will be something like 8,000. And if we use pin foundation, which means the foundation is very flexible, it may only be 1,500 and or so. So now you can see that the P delta effects or the stability of the structure, once you consider that in the analysis, the capacity reduces a lot and deformation is no longer linear, and we cannot apply unlimited loads anymore. This, however, is still not enough because we have not considered the capacity of the members that are involved in this deformation. We are not sure if the members can actually take this kind of load and deformation that we have shown here. So let's go to the next stage, which is the consideration of the capacity of the elements. And in this capacity-aware model, we can consider, or we should consider, the reinforcement quantity, its distribution, the cracking of concrete, the yielding of bars, and the failure of concrete at a given strain value, or whatever criteria we fix for failure. Still difficult to consider are bond and lap splice considerations, anchorage of reinforcement, local failures in materials, and damage to members and materials due to repeated loading and so on. So let's just consider the first part of this problem for now. How do we define capacity of a frame like this? Normally, the capacity can be defined by using two types of parameters. For a column, we can create the interaction diagram between axial load and moment, and from that, we can also determine the moment curvature for a given load level. So moment curvature, we have already discussed a lot in another video, and the interaction diagram we will discuss separately very soon. So these two important curves give us the capacity definition of the column, and this can include the confinement effects as well as the material properties and material strains and so on. Similarly, for the beam, we can draw or we can determine the moment curvature relationship, so that will determine the capacity. Similarly, we could have a shear and shear force curve that we could define to limit the shear failure, which we haven't considered for now in this example. Using these capacity indicators, capacity information, we can create a nonlinear model using plastic hinges, and we define lumped capacity at specified locations where we expect the failure to occur or capacity to be exceeded. And then we can also consider the stability effects that we already considered in the previous models, that means P delta, and we will use the fixed base for now. And you can use any analysis procedure. For example, nonlinear pushover analysis could be used to study this response. And if we do that, we will get force displacement relationship, something like that. And we see two curves here. One is with P delta and one is without P delta. And as you can see, without P delta, we have a higher capacity. With P delta, the capacity becomes even smaller as the deformation increases. And now you can see very clearly that the structure is actually not able to carry a lot of load. Now the capacity is only something like less than 3,000. The linear elastic model was showing something like 60,000 kilonewton. And now we see that after 2,500 or 2,800 kilonewton load, the structure will start to deform. And if it is including P delta, it will not even reach 2,500. And the load capacity will reduce rapidly as the displacement increases. So this is the important consideration where the capacity of the members comes in and alters the global response of the structure. And we can see clearly that the linear analysis was not able to capture this behavior. Now that we have created the models which were linear and models which were aware of the stability and the models which are aware of the capacity, let's see how do these models really compare with each other. And here you can see very clearly that the linear elastic model that we had first can give unlimited load capacity as the deformation increases. This was not very realistic, so we added cracking in it, and the cracking model gave us lower capacity, but still it was not really going to fail at any point. It will continue to give us that response forever. However, when we included the nonlinearity, which was the P delta effect, then we can see that the capacity actually was reduced quite a bit, and it could not go on as much as the linear models. And when we started to add the capacity considerations as well, so we saw that the load capacity of the entire frame actually reduced quite a bit compared to the linear elastic model. And actually the structure will be failing very early on, and the linear elastic response will completely miss all of the realistic response from this structure. If we focus a little bit more on the area which is of interest, because we are very large displacement like 400 millimeter for a structure of 4 meter is a bit too much. So let's see how does it compare with some realistic limits of displacement. First of all, let's look at the serviceability conditions. A lot of people will consider a drift of 0.5%, which is h over 200 roughly, to be a limit, and that will give us a displacement of 20 millimeter. So if you compare the displacement, the force capacities at 20 millimeter displacement, you will find that more or less all of the models are giving us the same value. So that means the nonlinearity, the stability is not a concern at this low load level or low displacement level of about h over 200 or 0.5% drift. So we get a force ratio between the nonlinear or the real response and the linear response to be roughly 1. And I'm comparing here the cracked section or the cracked response. When we look at the damage limit or damage consideration for a drift around 2%, which is often considered as the point where seismic design is to be performance-based design and other things have to be considered. So 2% is a rather large displacement drift limit for frames of this kind. At that level, about 80 millimeter of displacement, we get roughly a force factor of 3. That means the linear elastic response will give us a force value roughly 3 times the actual capacity of the frame if we consider both the section capacity and the stability effects or the P delta effects. And if we go to an even larger displacement, for example, about 4% drift, which is like failure of the structure, 160 millimeter, we will consider that to be the structure has almost completely failed. And at that point, the force factor will be around 8. That means the linear elastic model will be telling us that the structure will fail at a load 8 times more than it really will fail. So this is quite a large number. But at the same time, if you look at these numbers, they look familiar and they are related to the R factors or the structure response direction factors used in many codes. They are of similar order when the frames are designed properly. So the building codes and engineers working on the design for seismic effects are aware of these reductions and they are incorporated indirectly in some of the factors. But it's important to see that the linear response has its limitations and it cannot really predict the actual response even for a simple frame like we have considered here. Now that we have done quite a bit of nonlinear analysis, we can see that we have covered a lot of ground. Even though we have considered a lot of nonlinearity aspects, we only actually managed to consider 2 real effects: stability, strength and capacity. And we are still missing a lot of the other effects that can be considered for complete understanding of this frame. For example, damage. Sustained damage after a certain loading is applied and then unloaded or repeated loading, energy dissipation, long-term effects like creep and shrinkage that I mentioned, foundation settlement, soil structure interaction, local failures, and durability. So these are the things that we still haven't considered. If we want to go further, we can actually improve our analysis, nonlinear analysis, make it dynamic, make it more detailed, and we can consider the entire force deformation response, including hysteristics and the damage that comes from repeated loading. We haven't talked about the foundation. In all the cases, previous cases, we assume that the foundation will be some fixed support or a pin support. But let's look into that a little bit more detail. So let's start again with a simple frame. This is a very simple frame. And you can see here that this frame, this portal frame, if you apply the vertical load here, you will get this bending moment diagram in the green. And so if you use the fixed support here, you will get a bending moment at this location, at the support. And then to design the foundation, you will take that foundation, you will remove the fixed support, and you will replace it by a foundation. You will apply that load and bending moment, and then design the foundation. So when we analyze the frame, we throw the foundation away. and then we assume that the foundation is a fixed support. And then we calculate the bending moments and the floats, assuming it's a fixed support. Then we remove the structure, throw the structure away, and we bring those forces to a footing which is actually not fixed. This is capable of rotating, it is capable of settlement, it is capable of deforming, it is capable of doing everything. It is far from fixed. But that's what we assumed. So we got the forces assuming it's a fixed, and now we are trying to design a footing which is not, and we are applying the same forces on that. So we are actually over-stressing the foundation unnecessarily. Now let's go to the other side. Let's say we did not, so we say, oh no, this is not good. It should be pin. We start with the pin assumption. Then we will only get bending moment, only get vertical load and no bending moment. And we say, oh, I did a very good job. I reduced the size of the footing because now I only apply vertical load, no bending moment. So footing will become much smaller. But reality is that the column is not a pin here. Column is actually connected to the concrete footing with the bars and anchors and whatever, not. So in both cases, we are making an error of judgment. In one case, on the conservative side, and on one case, unconservative side, depending on how we look at it. So then, another problem, if you look at the formula for calculating bearing capacity, you will find that there are two things here which are needed: depth of the foundation and width of the foundation in some of the old formulas, which means that before even you can calculate the bearing capacity, allowable bearing capacity, you need the dimensions of the footings. And that is what we are trying to find from the analysis. So it is also interconnected. So of course you can get graphs and so on and improve this process. But let's get to this next problem. The real foundation looks something like this, or might look something like this. It is embedded in soil, it has dimension and so on. Now the question is, what is a good model for this foundation? Is this a good model, or is this a good model? Both of them, we can see, do not represent this footing, because this footing has dimensions, and this is not correct, that is not correct. What we need is here a model which is something like this, which can represent the rotational capacity of the footings, the vertical settlement of the footing, the horizontal movement of the footing. It can not only capture the deformation in the footing slab itself, but also capture the deformation in the soil below and around that. So, which means that we can create either a spring model like that, or we can create a spring model like that. Either way, we can represent the footing. So basically, this model should be actually applied here. And if we can do that, then we are a little bit closer to reality, or a little bit closer to consistency, I should say, if not reality. That means the two are at least consistent. The forces that you're getting in the footing and the structure response, they are at least compatible, not incompatible. So this is not really right. This is probably a little bit better. I wouldn't say right. And you can see from here that if you model a structure now complete with footing and springs and everything, rather than a fixed and pin or pin support, you get different answers. Let's talk about the basement, building basements and embedded structures a little bit, few minutes. So this is a small building, maybe a few story commercial building, and it has 1.5 basements. And you can see it's encased in soil here. So now on one side, the soil is providing it active soil pressure because of the hydrostatic effect of the soil. So we have this triangular pressure coming onto that. But let's say if you have earthquake on this side or wind from this side, now this pressure on the two sides will not be equal anymore, because once you have the active soil pressure, but you also have the passive soil pressure developing because of the building is trying to move to one direction and the soil is pushing back. So this side, the soil will push back, and this will create a reverse triangular passive pressure, which will add to this one. And this side, we don't know what's going on. Is it going to separate from the soil? Is the soil going to move with the building? What's going to happen? And when the force comes from the other direction, what will happen then? So we can see easily that the basement now is now in a state of stress, which is not the one that we normally would assume. It will vary on the lateral force. And there are formulas to calculate this passive pressure based on certain codes, and you can do that. So if you're going for earthquake, you can actually add that pressure onto the soil pressure, and you can account for that. But then we come to another situation. Let's look at the plan of the same building. And now we look at that, and we have soil all around that, right? So when the building starts to move in this direction, looking from the top, then this side front of the wall will try to stop it from moving. And the sides of the wall here will have skin friction also act a little bit. This may be small compared to that side, that resistance provided by the soil in the front. But if we move the building this side, then this side is very small, but the skin friction side is very long. That means the contribution of the skin friction on the wall could be significantly more than the passive pressure developing on the front of the building. So how do you account for that? How do you model this skin friction on the basement, which will not allow it to move in that direction? So many times we do not model these kind of things, and we rely on these passive pressures to do the modeling. But things can get more interesting. Let's say somebody, in the beginning, you made the building like this. Somebody came and they bought that plot, and they removed that soil and put their building there. Then all the assumptions that you made on the passive pressure and on the foundation are now gone, because suddenly that pressure is gone. Somebody made a building which is shorter or taller or deeper than yours, then your assumption, your soil resistance on that side is gone. How are you going to establish the stability of the building now on this side? And now your building might hit your neighbor. So you have to do impact analysis to make sure that your building doesn't hit your neighbor, or the neighbor building doesn't hit you. In many countries, there are rules on that you cannot do that. You have to prove by analysis that your construction will not affect the existing buildings. But in many other places, that rules may not be available. So you can create, your structure may change its behavior over its life. And even for simple conditions like embedment of a column or a pile within the soil, we can create many different situations which will affect these effective length, which will affect the slenderness, which will affect the bending moments, which will affect the lateral movements. So all of these things can actually complicate the analysis quite a bit. So unless we understand what's happening, we may not be able to estimate the response in a reliable manner. So like I said, the purpose of today's talk is to just raise challenges, be aware of what challenges are there in modeling, and how far the modeling can take us, and how far we still need to have engineering judgment incorporated into our analysis. Last few slides now. So what we can realize now is the bearing capacity is a function of footing size, and we have to be aware of that. Loads on foundation depends on how foundations are modeled. Foundation settlement should not be pre-specified, and modeling of basement is a tricky business. And you can make many assumptions about the basements, and you don't know what the future will do to the building. So we have to be aware of those. The solution to all of these problems, as I mentioned, are the links. NonLinear links and dampers and dashboards. So a combination of a damper which provides damping properties or damping mechanism, and a spring which provides the elastic response, and a nonlinear link which provides a nonlinear response. If you combine these three things together in the right order, in the right configuration, you can pretty much model any behavior if you understand them well. So this is the solution to all the problems that I have raised. Most of the problems that I raised actually can be modeled, can be handled by a combination of these three things together, putting them either in series or in parallel. That depends on the behavior, right? So we will have probably a full talk on how we use these nonlinear elements to model many of the problems that I discussed.
As I mentioned in the introduction, introduction that there is an important aspect of the construction that needs to be modeled as well, and which is the construction stages. As you know very well, that the structures are not built instantaneously, they are built over a period of time. So it is very important that we model this construction sequence and the time duration into our analysis, especially significant structures such as bridges and tall buildings, because this can significantly affect the results. What happens in reality is that when you are doing the construction, whatever deformations take place at any construction stage, they are corrected before the next construction stage comes up. For example, if it's a tall building, if there is an uneven settlement or the elastic shortening of columns and walls in a particular floor, during the construction, every floor will be constructed level. The previous deformations will not be continued. So those corrections make the structures be erected in a level and straight manner, which deviates from the analysis that we do. So if you look at a few examples, first of all, even if it's a symmetrical structures, and the deformations may be different between the central and the exterior columns in this case, and depending upon the height of the building, and that has to be accounted for by carrying out a construction stage analysis, which is not difficult these days. All you need to do is to define construction stages and in nonlinear case, and then run it. In programs like ETABS, they do that very quickly, and then you can simply run a story by story construction analysis. The problem becomes more significant when the structures are unsymmetrical. For example, you have shear walls on one side and no shear wall on the other side, then elastic shortening in the columns and walls will be different, and the structure may actually tilt. So the results that you will see in the normal analysis will actually be incorrect, because it will show you a large lateral deflection. But in reality, that will not be the case, because during construction, the structure will be built vertically. So those corrections may have to be done in the construction stage analysis. This also becomes important when the structures are especially built in stages, and the formworks are removed in stages. For example, a transfer girder or transfer beam, which will be temporarily showed during construction and removed at a certain time. So if you don't capture that, then the forces in the transfer system will be incorrectly captured. So it's very important that we realize when the construction stage analysis needs to be done, and then we do that analysis in the appropriate programs. And you will find now these days that the programs have a lot of capability to be able to do that. The second important thing is the long-term effects, creep and shrinkage, because they take place over 4, 5, 10 years. So the stress distribution and deformations may change over time, and that has to be captured by doing this long-term construction stage analysis as well. So I think both the effects of the short-term construction stages within a year and the long-term over 5 to 10 years need to be accounted for when we are dealing with complex structures or tall buildings and bridges. Let's now come to the last topic of this discussion, which is the nonlinear dynamic analysis. This is very important for two reasons. First of all, every structure, especially reinforced concrete, and every structure that we build becomes nonlinear at some point because of the material nonlinearity, because of the cross-section cracking nonlinearity, because of the geometric nonlinearity, and because of some members being overloaded and may become ineffective or become damaged more than the others. So the structure nonlinearity. So this nonlinearity, which happens at material, cross-section, member, and structure level, needs to be incorporated into the analysis. So that's why the nonlinear analysis is quite an important aspect of capturing the more realistic response. And second part, which is related but also independent, is the dynamics, because the forces induced on the structure because of the ground motion are changing with time rapidly, and because of that change, the inertial effects will come into play, and there will be interaction between the inertial effect with the modal response and the time history. So this complex interaction will alter the response of the structure globally as well as locally. And when this nonlinear, when this dynamic response is combined with the nonlinear, then we get to the complexity of doing a nonlinear dynamic analysis. At the present, as you know, this is considered to be the most accurate, or so to speak, realistic representation of the structural response. So whenever we compare any response determined from any other types of analysis, we always try to compare them against a nonlinear time history analysis, because it captures the variation of the ground motion as expected, and also the change in the nonlinear properties as expected. In this nonlinear analysis, we often use the expected properties, not the design properties, which could be very different, and that can alter the results quite a bit. And we capture the nonlinearity, we capture the capacity-based design, we capture the redistribution of forces, and so on. And it is captured on every time step as the structure continues through the history of its deformation and forces. So in this particular case, for the tall buildings, we model the beams, especially with nonlinear hinges, because they are the one that deform or yield most, and we rely on that for energy dissipation and providing the required ductility. And the shear walls, which we model by using multiple modeling options. For example, we can use nonlinear shell, we can use the fiber models, and we can use other techniques. So combination of beam nonlinearity and shear wall nonlinearity gives us the tool to capture the nonlinear behavior, and then we combine it with some realistic ground motions that we can determine based on the response spectrum of that particular site, or we can carry out a site-specific investigation to determine more realistic time histories, which are in accordance with the geotechnical as well as the seismic effects in the region of the soil and the bedrock and the source and all of those things. So I think nonlinear dynamic time history analysis is the ultimate, which combines all of the issues that I discussed, plus a lot more. So when we are able to do that, that means we have reached, so to speak, currently the state of the art in structural analysis and modeling. So I hope that this discussion will help us to move towards more realistic modeling. Now that we have seen some of the discussion on these topics, let me just conclude by saying that it is not easy to model structures realistically and accurately, even simple ones, if we want to capture all the response. So in reality, what we need to do is, first of all, to be aware that what we are modeling is not true representation of the structure, and the results that we are getting are only for the model that we created, not for the structure. And once we are aware of these limitations, then we can make adjustments in the way we interpret the results, and also the way we adjust them by our engineering judgment, so to speak. So I think it's extremely important that we are aware of the limitations of our model analysis, and we are able to take them into account when we do the final design. And I often say to our colleagues and our students that try to model what is going to be built, or you should construct or build what you have modeled. There should not be much difference between what you have modeled and what has been built, because the structure will respond to the conditions that it has been actually built, not on the assumptions that we made in the modeling. So I hope this has been some interesting discussion, and now we can go back to some questions from this discussion. Thank you so much once again, and it's been a pleasure for me to be able to talk on this convention. And I look forward to coming back to Manila and seeing all of you hopefully in the next one.